Marcin is a third-year PhD student in theoretical physics, and he's studying at the Department of Physics and Astronomy at the University of Wrocław in Poland. He's interested in studying scalar-tensor cosmology, especially scalar field dark matter models, the likes of which are fuzzy dark matter and axionic dark matter. And he's also interested in alternative hypotheses to cosmological inflation, like bounce cosmology and cyclic models, which I think he will both touch today. And today he will be presenting his work that's titled, "Is it possible to separate baryonic from dark matter within the Lambda-CDM formalism?" And his article will be also, the link to his article will be also appended to a chat here and will be also available on the Slack channel. So that's about all I had to say. So Marcin, feel free to take the stage, and we're looking forward to hearing about your work.
Okay, thank you very much for the opportunity to give a talk at CosmoVerse JournalClub. So today I would like about dark matter in scalar-tensor cosmology, and my talk is based on the preprint which I wrote with my supervisor, Professor Andrzej Borowiec, and the title you can see here. Okay, so let's start with the basis of the Lambda-CDM model. So in the Lambda-CDM model, we assume that the constituents of the universe are dark energy. So in fact, in LCDM, the cosmological constant, dark matter and baryonic matter, which are treated as dust or matter, and a little of radiation. So in fact, we have no idea about 95% of the universe. That's the so-called dark sector of the universe. So today I would like to say something about dark matter. So of course we have lots of evidences of existence of the dark matter. For example, the famous rotation curves of galaxies, gravitational lensing, as you can see here, it's the Webb first deep field. Of course, analysis of the cosmic microwave background, and maybe the existence of the high redshift galaxies, which were observed by the cosmic Webb telescope. Okay, so in fact, you could think about the problem of dark matter in sense of some cases of modified gravity, for example, tensor vector scalar, which I will say something more, light bosons, just as, for example, fuzzy dark matter, neutrinos, weak scale, other particles like WIMP-Zillas, and the macroscopic scales. So I would like to start with the most general action for the scalar tensor theories of gravity. So here you can see the four parameters, the four frame parameters. A of phi is a coupling between the scalar field and the geometric segment of the action. B of phi is just the kinetic term, which you can observe here. V of phi is, of course, a self-interaction of the scalar field, and alpha of phi is the function which describes the non-linear coupling between the matter part and the scalar field in our scalar tensor theory. Okay, so in fact, in theoretical cosmology, we have two main so-called conformal frames. The first frame is the Einstein frame, in which we have non-minimal coupling between the scalar field phi and the matter part. So we modify the matter segment of our theory. So the Einstein-Hilbert term is the same as in Einstein-Hilbert action. And in such a case, if we have non-minimal coupling, we obtain the chameleon mechanism. So in fact, we have no conservation of the energy momentum tensor. So you could observe that here is some non-zero value. And in fact, the matter particles followed the conformally rescaled geodesics. So this is also called as the fifth force. And the second frame is the Jordan frame, in which we have non-minimal coupling between the scalar field and geometry. So here we have no coupling between the matter part and the scalar field, but instead we obtain phi-dependent effective Newtonian constant. Okay, and of course, there is a problem with the question which of this frame is physical, or maybe none of them. Okay, so we start with the standard Friedman-Lemaitre-Robertson-Walker metric with the lapse function, so the reparametrization of the cosmological time. We plug the energy momentum tensor of the form of the perfect fluid. So if the derivative of the alpha function is 0, so in fact, if alpha is constant, then we obtain the standard form of the continuity equation in cosmology. And in fact, we have the dependence of energy density and pressure in terms of just the scale factor. But if you think about the non-minimal coupling between the matter and scalar field, you don't obtain the standard continuity equation. Instead, you obtain the non-zero right-hand side of the equation. So here you have this formula. So in fact, your energy density and the pressure depends not only on the scalar factor, but also at the scalar field. Okay, so now let's think about the non-conservation of the energy momentum tensor. So we introduce the notion of the so-called generating function. So we called it as f of x, and it's non-negative for x, which is non-negative. This comes from the positivity energy condition. So we can introduce the notion of the g of x function, and f of x and g of x could describe the energy density of our fluid and the pressure of our fluid, and vice versa. If we know the form of the g of x, we could obtain the form of the f of x, so in fact, the energy density. Of course, in such a notion of the generating function, we could obtain the standard equation of state parameter, which is such a formula, and the square of the speed of sound in such a case. And in fact, for each of the f of x and g of x, we obtain the extensions with two additional parameters, a and b. And b, of course, must be non-zero. So, for example, if you want to introduce this notion to one of the examples, if you plug such a function, f of x, so the notion of the energy density, you obtain such a function which describes the pressure. So we obtain the generalized logotropic fluid, so one of the dark fluids, cosmology. Okay, and one of the main, let's say, conclusions of our paper, we obtained the explicit form of the non-minimally coupled energy density and pressure of our fluid. So if rho and p are the solutions of the standard continuity equation, then such formulas are the solutions of the non-continuity equation. So in fact, the equation number 14. Okay, so of course we can apply it also to the n+1 dimensional space, and then we obtain such formulas. Okay, so what are the conclusions comes from our formalism? In fact, in most approaches, the authors assumed ad hoc that the chameleon mechanism manifests itself as just a multiplicative factor in front of the matter Lagrangian. So here you can see e to the alpha of 5 times just the function rho of a. But in fact, this is true only in the case of non-relativistic matter, because in the case of a dust, cosmological dust, rho of a is proportional to a to the minus cubed. So if you take another form of the rho of a, then you don't obtain just the multiplicative factor and rho of a. So the remarks. The first part is just a generalization of the results from the study of Chauvanny, so the logotropic dark fluids. But the notion of the non-minimally coupled energy density and pressure are new. Of course, you can observe that in such an approach, we can generate a large class of possibly unphysical functions, but we can control it by the energy conditions. And if we treat the scalar tensor theory as an effective description, then at least some of them are physically acceptable from the point of view of the unknown, more fundamental theory and or additional fields. Okay, and if we apply our generated function formalism to the energy conditions, and here you can see the explicit formulas, then at least from the mathematical point of view, the strong energy condition and null energy condition admit negative energy densities. So in fact, the negative values of the generating function for the non-negative x. So maybe it's just mathematical artifacts, or maybe some kind of footprints of the quantum gravity theories or new types of matter. It must be research later. Okay, so now let's go to our models from the preprint. So we start with such an explicit form of the action with the epsilon parameter, which could take the -1 value for the so-called phantom ghost scalar field and +1 for the so-called scalaron quintessence. So we take just a cosmological constant as the self-interaction potential, and the non-minimally coupled function is gamma natural logarithm of phi, so we obtain the power law non-minimal coupling. And from the constraint equation, we obtained the correct ratio of the dark matter to baryonic matter densities. It's in our model, it's just nowadays value of the scalar field to the power gamma. So here you can see the Friedman equation and the Klein-Gordon equation with the additional epsilon and additional segments coming from the non-minimal coupling between baryonic matter and the scalar field. And now let's think about the relevant cosmological aspects of the phantom ghost scalar field, because in the case of the phantom scalar field, the equation of state parameter is less than -1. Yeah, so in fact, such a field could be obtained from the Reinhold models, Browns-Dick theory, and the Sitter CFT. And in fact, it is just a scalar field with a negative kinetic term, so-called the wrong term with the scalar fields, and it comes from the 2A string theory and the low energy limit of the 12-dimensional type 2B action. And what is important? Important is the fact that the value of the phantom energy density increases with time in the period after the cosmological bounce. Okay, so how one could interpret dark matter in our Einstein frame scalar-tensor scalaron and Einstein frame scalar-tensor ghost models. So the baryonic matter, as in the standard case, is conserved. So here you can see the continuity equation. But the dust, so the standard matter is not conserved, because here you can see the additional segment, which is just the scalar field, and we obtain the non-continuity equation. And the right-hand side of the equation is non-zero. So in fact, in our approach, dark matter could be called as chameleon dark matter, which is a energy density of the dust minus the energy density of the baryonic matter. So in our case, it's just an emergent quantity whose density is not conserved. And of course, one could introduce the notion of the effective potential, and you can see the additional segments comes from the kinetic energy of the scalar field and the non-minimal coupling between the scalar field and baryonic matter. And here you can see a figure which shows you the notion of the effective potential. So in the case of Lambda-CDM and the scalaron, so the model with the +1 value of the epsilon, you can't observe the local minimum. But in the case of the phantom ghost field, you can observe the local minimum, which could be potentially treated as the reheating moment of the universe. Here you can see the evolution of the scale factor in our models. So in the case of the scalaron, we also have the problem with the Big Bang and the lack of the inflationary mechanism. But in the case of the phantom ghost model, we obtain the so-called matter bounce scenario. And how you can see it? Of course, in the case of the Lambda-CDM and the scalaron, we observe, say, the standard evolution of the Hubble parameter. But in the case of the phantom ghost, here you can see that in some moments before the bounce, one obtains the global minimum of the Hubble parameter. Then at the bounce, we go through the zero value. Then when the bounce is ended, we obtain the global maximum, and then we tend to the standard Lambda-CDM evolution during the cosmological time. Okay, and what is the mechanism which we could treat it as the main, let's say, constituents which give us the matter bounce? So here you can see the effective phantom energy density. So you can see that when the universe contracts, then you obtain the maximum value of the energy density in the phantom model. But when the kinetic energy of the phantom field, say, turned on, then it gives the negative notion to the energy density. So the effective energy density goes probably to zero or maybe some small value. So here you have the bounce moment. And then when the kinetic energy of the scalar field turned on, we obtain the same maximum value of the energy density as before the bounce, and then the energy density dilutes as in the standard Lambda-CDM model. Okay, and here you can see the evolution of the scalar field equation of state parameters. So in the case of the scalaron field, we obtain the notion which is similar to the quintessence scenario. So in fact, after the probably big bounce, the omega is just 1, so we obtain the stiff matter era. Then we go to the standard dust evolution, so omega is 0, and then delay time we go to the -1. But in the case of the phantom scalar field, we have the stiff matter era in which we have the so-called matter bounce, but we have some kind probably of phase transition, because after the stiff matter era, we obtain the phantom evolution. So we go from the more negative values of the equation of state parameter, and at delay time, we go to the standard -1 evolution. Okay, so what are the conclusions of my talk? So first of all, from our formalism, we could think about the revision of the chameleon mechanism, because in general, we are not dealing only with a multiplicative factor before the energy density, but we also must rearrange the scalar dependence in rho. Secondly, in scalar tensor theories, there is a possibility of separating the influence of baryonic and dark matter in the evolution of the universe, at least at the background level, of course. And according to our effective description, in such a case, dark matter is just an emergent quantity. It is non-minimally coupled to baryonic matter, and its energy density is not conserved. Okay, and what are the perspectives? First of all, we should think about, of course, the analysis with the dynamical systems method and cosmological perturbations to see what is happening, let's say, with the bounce or with the Big Bang in the case of the scalaron model. Of course, we should also think about the incorporation of a non-trivial, non-constant form of the scalar field potential. So, for example, the scalar field dark matter models, and here you can see one of the examples. So it is called axiomic dark matter. So one of the approaches from the alter-like bosonic dark matter. And of course, we also could think in the further times about the models which are alternatives to cosmological inflations. For example, matter bounce, pyrotic universe, and the cyclic scenario. Of course, so that's everything for today. Thank you very much.
Right, Marcin, thank you very much. Very nice presentation.